Okay, good evening, ladies and gentlemen, dear colleagues, dear students and friends. It's a pleasure to welcome you this evening to the Cacoullos Memorial Lecture here at the University of Macedonia. This is a joint event organized with the Analytics Program, the Laboratory of Quantitative Methods, the Hellenic Statistical Institute, and of course, colleagues from the Departments of Informatics and Mathematics at the University of Thessaloniki. This lecture has a special meaning for many of us, and for me personally, because it is dedicated to the memory of Theophilus Kάκουλλος. Since I'm sure that most of you don't know what is Cacoullos Memorial Lecture, I need to say a few words about our professor, our late professor, Theophilus Kάκουλλος. Theophilus played a truly defining role in the development of statistics in Greece. Professor Kάκουλλος was one of the key figures in establishing the field of statistics, probability and statistics in this country. He was, in fact, the first professor of statistics back in the 60s in Greece at the University of Athens. He helped sharing not only the discipline itself, shaping the discipline itself, but also the academic community around it, and also was one of the founders of the Greek Statistical Institute, the Hellenic, as we say, Statistical Institute. I remember back in 1897, I was a PhD student, and we have the first three-day event of the newly formed Statistical Institute, and it was back in the 80s, as we say. My first experience by delivering a talk in such an event, in a conference, so to speak. Although I didn't have the chance to attend his lecture since he was a professor at the University of Athens. I had the opportunity to know Professor Kάκουλλος and attend his talks in conferences, seminars, and various meetings. We also share a common origin, as we are fellow Cypriots. Those who work with him, and there are a lot of them, often speak not only about his scientific contribution, there are also some methods and techniques named after Professor Kάκουλλος, but also about his character, of which I have personal opinion, his directness, and his genuine support for younger researchers, including me. He was known for his humor that came naturally, not by effort, and for lectures that were always enriched with observations and remarks that always went beyond mathematics and stayed with you long after. So it is therefore very meaningful that this lecture series, which are made possible through the generosity of his family, who provides the relevant funding, continues to bring distinguished scholars to engage with our community. And this brings me to today's speaker. We are truly delighted to welcome Professor Sylvia Richardson to our university. Perhaps you read the leaflet. Professor Richardson is internationally recognized as one of the leading figures in biostatistics. She's Professor of Biostatistics and Director of the MRC unit at the University of Cambridge, and has made fundamental contributions to areas such as Bayesian modeling, clustering, and the analysis of complex health data. She was awarded the Guy Medal in Silver by the Royal Statistical Society. Wow, the Royal Statistical Society. All of us who worked in statistics, we always covet to send a paper for the Royal Statistical Society Series C, I think, anyway. And also he was honored as Commander of the Order of the British Empire. That sounds very honorable, dear Sylvia, anyway. So we need to call you Commander from now on.
Absolutely.
We only know 007 as a commander. For services to medical statistics, and also served as president of the Royal Statistical Society in 2021 and 22. Her work was consistently bridged methodological development with real-world impact, particularly in the fields of genomics, precision medicine, statistical thinking is essential in these fields. And what makes her presence here especially fitting to our programs, the MBA and the analytics program that jointly, along with the other colleagues, are organizing this memorial lecture, is that her work reflects exactly the kind of connection between theory and application that this lecture series is meant to highlight. So, Professor Richardson, we are very honored to have you with us. Now, let me invite my colleague, Associate Professor Leonidas Hadjithomas, to also offer his welcome. Then he will be followed by Emeritus Professor Polychronis Moisiadis, my tutor back in the 80s, a scholar that I personally, I'm very glad to see him here today. Professor Moisiadis joined us on behalf of the Hellenic Statistical Institute. And after that, I will briefly present the results of the usual poll that we made on LinkedIn before any of our talks. So, Leonida, you have the floor for a while. Thank you.
Good evening, ladies and gentlemen, dear colleagues, students, and guests. It is a great pleasure to welcome Professor Sylvia Richardson to the University of Macedonia this evening. Professor Richardson is widely recognized as one of the most distinguished figures in contemporary biostatistics. She has served as director of the MRC Biostatistics Unit and has held a research professorship at the University of Cambridge. Earlier in her academic career, she also held senior positions at Imperial College London and the French National Institute of Health and Medical Research. For the Master of Business Analytics and Data Science is a great honor. This lecture is especially meaningful because it reflects something we strongly believe in, that analytics and data science matter most when they are applied to important real-world problems. Events like this are important because they bring our students in contact with outstanding scholars and with the broader spirit of interdisciplinary research and collaboration that is in the center of our program, the Master of Business Analytics and Data Science. So, Professor Richardson, we are truly honored to have you with us this evening here in Thessaloniki and at the University of Macedonia. Thank you very much for being here, and we are looking forward to your lecture. Thank you. Professor.
Dear colleagues, dear Mrs. Richardson, my old students, my friends, I would like to welcome you on behalf of the Greek Statistical Institute to today's event in the memory of Kάκουλλος, Θεόφιλος Κάκουλλος, who in those days in the United States of America, he was known as Theo, only Theo. And all the people understood for one of whom was the we will have the pleasure of listening to Dr. Sylvia Richardson, Professor of Biostatistics in the University of Cambridge, trying to uncover, trying to explain to us how to uncover health data. We are looking forward to this interesting talk.
So before we hear from Professor Richardson, we will share some results of the poll that we always run ahead of our evening events. Do we have the, I need the, okay. So this time, we asked, in your opinion, what is the main way advanced analytics creates real value? The poll was conducted, as usual, on LinkedIn and drew participation from professionals and higher education graduates. The options were, fortunately, on LinkedIn, you can only put 4 options and only at most 30 characters. What kind of poll is that? I don't know, anyway. So the 4 options were discovering meaningful patterns, linking data to outcomes, turning insights into action, and better decision-making. And better decision-making was voted about half of the respondents, about 50%, who chose better decision-making. And then the second one was turning insights into action, came second at 24%, followed by meaningful patterns, 16%, and linking data to outcomes at a tiny 11%. Now, what is interesting here in this poll is that the result, the top answer, along with the second one, better decision-making and turning insights into actions, more or less are similar. Yeah? You making better decisions means like that you, the insights that you make out of data, you turn them into actions. So they are connected. They have somehow, not causality, perhaps a correlation, Panagiotis. What to say about that? Anyway, so, but actually, the actual decision-making is, in a sense, the final goal, the output, isn't it? So today's talk, in my opinion, is about what happens before the final decision-making. How do you discover patterns and meaningful ideas? It's about the remaining 16 and 11%, I think, Sylvia, isn't it?
Yes,
So
it is.
today's talk is about the hidden percentages of how we take advantage of our data to reach better decisions. So, and on that note, Professor Richardson, the floor is yours. Thank you.
Thank you so much. Is the microphone, can everybody hear me? Okay. Yes. I'm very, first I want to thank Professor Georgiou, the member of the Greek Statistical Institute and the members of the Cacoullos Memorial Lecture for inviting me here. I've been here now a week. This is the second lecture, second memorial lecture, and it's really a great honor to be here with you. I chose to, some of you might have been to my previous lecture, and I really chose to talk about a separate topic, the topic of basically clustering and uncovering patterns, a topic that I've been thinking about for a few years, at least I would say over 15 years, and which keeps coming back up in different guise and forms. So I'm going to try to illustrate some of the thinking, and I will have quite a lot of examples and hopefully a little bit of notation, but not too much, just to anchor things. It's very hard to talk without any notation, I find. But I'm trying to really motivate more the different points of view one can take. So I've got basically four, just here, sort of four main sections. And what I wanted to start with, no, I don't want to go through those. What's going on? No, it's not going well. No, it's gone right to the end. That's not really going well. No, I'm right at the end there. No. Go back right to the beginning. Yup. So how do I get the next one? Okay, start again. Just this one. Okay, just this one. So I wanted to acknowledge some colleagues in Cambridge, which I have, in particularly Paul Kirk, a PI in Cambridge, which I've been working with him on the topic of clustering for many years, but also other contributors, ex-postdoc, colleagues which are now at other universities, and of course funding from the Medical Research Council. So now clustering and classification have a long history, and it's pretty natural to try to break down heterogeneity. We are surrounded by heterogeneity in many guise and form. To find meaningful patterns, it's something which has confronted us for many, many years. And it's an important, particularly appropriate place here to make a reference to the great philosopher Aristotle, who was born not far from Thessaloniki and who had a profound interest in classification. So now I'm going to try to read to you this quote in ancient Greek. And please, I apologize because I never learned ancient Greek, only the symbols for doing mathematics. So, uden atakov ton fishi. And I've got the translation. I've got the translation in modern Greek and also the translation in English. Basically, he was saying there's nothing disordered in the things of nature. And this quote was given to me by Christos Baltas because we had a very interesting conversation over dinner about Aristotle and our love of philosophy, basically. So, but I'm not going to try to do hard classification. In fact, the whole of the lecture is trying to consider a much more flexible way of clustering, which is called model-based clustering, and which recognize that this is hidden structure and we can never know the truth. And so you basically want to explore different likely clustering patterns. So indeed in health sciences, as well as in business and many other sciences, we're constantly confronted with sorts of heterogeneity which go from the micro, like our genetic makeup, we definitely are heterogeneous, to very micro level, the way we have our lifestyle, the environment we're surrounded with. So studies typically record many sets of variables which in the health science, you often call them covariates. It just means variables, often highly correlated. And one of the first things is to try to see, is there main patterns, like covariation, basically, among sets of related variables. This is useful for dimension reduction because you try to partition the subject into more homogeneous group. I put that in quote because it's not. I'm not making that very precise for the minute. According to the profile. So when I talk to profile, I will talk the set of variables and how between one individual and another one, how their profile for the values of these variables are quite similar. So as I was saying, we will not use rule-based classification. We give Haas threshold in which, like a classification algorithm, deterministic. We want to use statistical model. And the twist, and maybe something that you have heard about less, is that I'm trying to also link some of these clusters with outcome. So in fact, do some kind of joint modeling of, so the clusters, the formation of the cluster will be informed also whether they're actually predictive somehow of outcome. Among all the possible way of clustering, this twist, doing this joint modeling, provides often more interpretability. Whoops. How do I go back then? Maybe this one? Yes. No, but I was right then anyway. So there are many aspects of clustering. So unsupervised clustering, when I'm not considering an outcome, is a really ill-defined problem because there is no ground truth. The whole point is there is no ground truth. So there will be sensitivity to some of your modeling assumptions, and particularly that will influence possibly the number of clusters you end up reporting. So it's important to keep that in mind. To incorporate uncertainty when you report results. And also sometimes it's useful to try to find which of the variables, but I won't have time to really talk about that, which of the variables are the more important for the clustering. Not all variables are as informative as each other. And now when we additionally introduce an outcome, I call it now outcome-guided clustering, we're trying to find, in fact, useful or interesting or useful structure in the way that they actually find clusters which put together individuals would also have similar outcomes. So you need to choose an outcome or several outcomes together. So this is a way, in a way, because there's so many ways of partitioning, this is a way of trying to tease out more useful or interesting clustering structures. So these are and I'm going to first talk about very basic definition of what I call model-based clustering with a type of sort of semi-parametric approach which doesn't particularly want to specify exactly the number of clusters. So just a little bit of notation. Zi is it's a latent variable. If I have a clustering structure, if I say Zi equals C, it will say, it will allocate the I subject to the C cluster. And then there will be these mixture probabilities. So the partition, each of the group C will have a probability. And this is defined by psi index C. Now let's think about the profile of covariate. So let's say you have you're interested in smoking. I'll come back to smoking in a minute, that's one of my examples. But it's not just smoking, there's a whole lifestyle. So you've got three variables: smoking or not smoking, drinking, and exercising. So for what I would say a covariate profile for an individual is just these values: that person smoke, doesn't drink, and exercise. So in each cluster, when I break down the population, there will be cluster-specific multinomial probability, basically, of the people in the cluster on average with probability so and so they drink with probability. Another cluster will be a different probability for them to actually drink or exercise and so on. And phi is going to be, so phi C and P will be the probability for cluster C and concerning the variable P, because I have a whole bunch of variables, and when I put all these multinomial probabilities together, it's basically denoted by phi. So how do we do this cluster? Basic model-based clustering gives a probability at the whole vector of the variable, and then the simplification there is saying that conditional on the cluster, conditional basically on being within a cluster, there is independent assumption. The probability of having the categories become independent. Of course, marginally, they're not independent, but conditionally on the cluster, because I have this discrete covariate, I'm making this assumption that they actually multiply. For the actual cluster themselves, we use a flexible non-parametric model which doesn't assume, which could supposed to have an infinite number of clusters. Of course, it'll never be infinite because you have a finite population, but you don't want to basically necessarily say restrict it to a finite number. You want a loose probability structure, which is called the stick breaking, which basically saying the first cluster has probability P, and then that's the first part of your stick, then you break again what's left, and that's your next probability, and so on. And you could see that just piles up to sum up to 1, but it doesn't necessarily. Of course, we will truncate that in practice. So if you put these two things together, the model for the actual probability of the cluster, the psi, and the model for the variable, you've got this joint, basically. This is the most basic non-parametric, but basic non-parametric model for a cluster, a clustering. Right. And we have developed software to actually implement that, which is called Premium, which deals with not just categorical variable, but also normally distributed covariates. It's got a truncated DP version, etc. And so now I'm going to talk to describe how we now extend it to include the outcome, quite simply, and then look at 2 case studies. Often when you do a clustering exercise, whatever method you're using, you try to typically validate it by looking at your cluster and say, oh, well, maybe there's this other characteristic, this outcome, that actually this individual share. And then you say, oh yeah, my clustering makes sense because they are sharing this characteristic. So this is like post-validation. So the question is, why not use that directly in the model and doing a joint model? So that's, as I was saying, we're doing this joint model to really guide, because to guide towards more interesting structure and more meaningful partition. So we've called it profile, a first version of this model. So that's like 210, was developed with a colleague. And we called it profile regression because you could think of it in a way as linking the outcome with a profile of an individual. In fact, one of these group characteristics. But it could be also called outcome-guided clustering. We started with profile regression, then we sort of switch a little bit to because it's a bit obscure, to outcome-guided regression. So in this, I don't think I've jumped. No. So in this version, we now have, in this model, so we had Xi, the profile. Now we've got a Yi, which is an outcome. For the moment, I'm thinking univariate. And we also can have, of course, some fixed effects, some covariates, which are not part of the clustering, but you want to adjust, which are predictors, known predictors of Y, and you want to take them into account. But basically, this statistical framework of outcome-guided is this joint model. So now we've got, I'm summing over all the cluster. This is psi, the probability, the mixture weight for cluster C. This is given that Xi is in cluster C. This is the distribution of the covariate vector, and I'm multiplying now by the probability of the outcome given a random effect or a vector of random effect which characterizes the influence of the cluster on the Y, and given also some fixed effects. This is very simple. So for example, if I had a Bernoulli outcome, I could have a logistic model which saying that the probability of having the probability of Y equal 1 is going to have a random intercept plus the standard thing, and this random intercept is linked to the covariate, to the cluster to which all the covariate Xi are putting this individual. So this is through this random effect that we are linking basically the cluster and the profile and the outcome of Y. And again, note that here we're making conditional given the clusters. These two parts are conditionally independent. Again, they're clearly not marginally dependent. So basically, this algorithm, which is coded in Premium, it explores, I haven't put the priors and all sorts of things, but it's a Bayesian output, and it explores basically, it churns out posterior clustering samples in the right probability. But, it's a very rich output. So, one iteration, the people are distributed like that, the phi are this way, and so on. Next iteration, people get reshuffled, the phi's change, and so on. Now, and it's representing the uncertainty that you have, basically, what is the true clustering. But you do need to actually try to output something which people can interpret. So you need to try to get a best partition in the among all these a posteriori. And you also want to not just give one best partition, but gives some kind of uncertainty for some of the quantities associated with this partition. And you could also use the output to predict what would happen. Now, I'm inventing a new profile, and that's really very powerful, because to try to understand what's going on, you could invent a new profile, run it through the algorithm without it contributing to the algorithm, and you output its Y, for example. And so you could investigate the effect of any profile and contrasting profile to try to see what is really the effect of this whole bunch of covariates on my outcome. Now, one issue is that which is always the difficult issue in clustering, is that from one iteration to the next, you cannot name the clusters. The clusters are there, but all you get is one partition, say with 10 clusters. Then the next time you get a partition with 12 clusters, and you can't say this is cluster 1 and this is again cluster 1. That is totally meaningless. They don't have labels. There's no label in this business. So how do you actually produce something? How do you produce a good summary? Well, you need to find what's invariant. And what's invariant is the similarity matrix, i.e. what you could measure at each iteration is take all the pairs of individuals, and you could see whether they are or not in the same cluster. And you could track that, and that doesn't matter that whatever the cluster is labeled. You're just taking individual and tracking them and looking whether or not they're in the same cluster or not, and then you record that throughout for all the pairs, and then you've got this posterior similarity matrix, which you could try to then characterize and summarize. And so there's many ways of actually try to find partitions from that posterior similarity matrix. We chose one in our algorithm, which is called PAM, partitioning around meloids, but you could use any routine that you want to actually, but the key element there is this posterior similarity matrix, which is independent of any labels. And also, so first example I want to discuss is something we did with a colleague of mine way back in Paris, who was an epidemiologist, and she was really interested in lung cancer and all sorts of things connected with lung cancer. But as part as her studies, she had detailed smoking history, and typically epidemiologists they collect detailed smoking history, but then they make it into a cumulative index, which is pack years, and they just have a sort of function saying what's your risk with respect to the pack years. And she had some questions like, well, really, pack years, you could have the same pack years if you smoke not much but for very long, or if you smoke it really like a trooper for 10 years. So what's more at risk? But these variables are how many you smoke and how long you smoke, they're extremely highly correlated. And if you try to do regression on that, you get a lot of nonsense. So she said, can you try that? Can you cluster the profiles of smoking? And we tried, and it actually basically works. So this is just a small, what do you call it? Just it's not the true output, but it's just to say what we were trying to do. We were trying to basically find whether if there's these three quantities: cigarette per day, the time you've been smoking, and the starting age, and you were trying to see whether different patterns of which all give you the same number, possibly some give you the same number of pack years, but do they give you the same risk? And to do that, in fact, the simplest for us was, so when we analyzed her study, we had 9 groups, 5 higher risk group, 4 lower ones. I don't display you the results because you just need, it's the complicated output and you really need to ponder on it. But what I'm going to show to you is more, I've chosen different combinations of a covariate profile, and just to contrast basically the differing role of intensity and duration of smoking, and to see what effect. So here at the bottom we've got four category of intensity, and here we've got increasing duration, and if all the curves, they actually go the right way. The longer you smoke, the more risk you have. These are the intervals of the risk, and the more you smoke of cigarette per day, the higher your risk is. But look, with respect to actually number of cigarettes, there is a leveling off. Whether with duration we have actual jump. So duration seems to be more important in a way in creating the risk than the intensity. And you could see that also on other plots where we compare profile. As I say, we can create profiles. So artificially, we create a profile of people having 45 years pack years, but either having low intensity and high duration. They get to that because they've smoked for low intensity, not that much, but for very long, or they smoke for a lot for a few years. And clearly you see, and this is kind of the prediction, the posterior of the risk of this. So it's the same pack years, but different profile of smoking. And you could see that duration is worse than, concentrate on the higher risk than high intensity for a short time. So this is one example of how you could use clustering to really decouple these very correlated things, which are very hard to decouple by standard regression or something like that. My second example, completely different type of data, they are geographical data. They are basically around London. They're basically, again, lung cancer. I don't know, I'm not absolutely an expert in lung cancer, but it's basically lung cancer by small areas, so roughly 5,000 small districts in London, which have been all characterized both by air pollution, and in particularly this small particulate matters. In fact, now people consider much smaller than that. By that time, it was PM10. By type of whether the areas are quite deprived or not, by recording 6 domains: average income in the area, non-employment rate, health, education, housing, and crime. So capturing deprivation by the 6th domain, ethnicity, and then the outcome was the number, basically, of death by lung cancer, and you had an expected number following the demographic like usual. And so typical analysis, you do a Poisson regression of basically the observed number of cases with respect to the expected and all these covariate. And when you do that, what do you get? You get a negative, more or less, effect of air pollution, which just possibly doesn't have any effect, but it shouldn't really be negative. And so, yes, what I forgot to say is that typically the 6 domains that I had highlighted are typically combined into a global index of deprivation, which is a combination. And this is what went in this model, IMD, this index of multiple deprivation. And in this case, if you do the standard Poisson regression, you're getting this weird result, and makes you think you haven't really adjusted carefully for the deprivation. This kind of combined index doesn't really do the job when you're just adjusting that in the regression. So why not try to do a outcome-guided clustering where we have the Poisson model here, where that's the typical Poisson model, but then instead of combining into one index of multiple deprivation, we keep the 6-dimensional vector of income, employment, these are all proportion or quantiles of something, and we actually we cluster those, and here is the map. It's actually fine. It needed 9 clusters. You could see the heterogeneity and how these are not all in the same area and stuff. There's a lot of heterogeneity of deprivation in London. It can really change quite drastically from one neighbor to the other. And do this outcome guided. So we've got this joint model where we're clustering the 6 indices, and then this is feeding this, in the Poisson regression, this cluster-specific intercept. And there, when you do that, suddenly, well, not suddenly, but as we were hoping, the coefficient of PM10 now becomes positive, barely significant, but definitely it goes the right way and the expected way. And there has been many other studies. So just to show the advantage of not summarizing, so it's a second example where instead of summarizing a complicated, what you would say, exposure profile with correlated variable, you're better off putting that in a clustering model and basically using the actual clusters as for stratifying. And it's better to put it in a joint model. You could nearly do it in a 2-step if you wanted, but there, the joint model, we're basically informing, it's better for the uncertainty. My third topic is just expanding basically the profile regression with longitudinal outcome. Those who were at my first lecture, where there was a lot, I discussed quite a lot of longitudinal outcome. These are very valuable type of data, in particularly in health, but in many guys. So what do we want to do? Well, we want to sort of expand the model to consider the YI, which so far it was either a Bernoulli or it was a Poisson, so it was discrete, to be a whole vector of measures at different time points. And again, we want to jointly cluster some covariates and the longitudinal outcome. So this is just the, so we have basically a cluster C of which basically feeds in longitudinal outcome and the profile variables, which can be not only categorical but also Gaussian. And the longitudinal outcome, avoiding to try to choose a parametric model, I'm still staying in the sort of realm of as non-parametric as possible. We just make assumption of smoothness and use basically Gaussian process. So again, I'm talking about, so imagine as a toy example, this is the entire population, but you could clearly see two subpopulations. And so basically you're trying to find these two modeling those following some characteristic of these patients and what feeds in. So we will characterize each of these subpopulation trajectory by a latent function. We only make basically smoothness assumption on that function. And so this was my original model. And now for the yi, this part of the model, it's now becoming a whole, if you've got a few time points, it's becoming a whole longitudinal trajectory of which we have a Gaussian process indexed by C, which so it's a cluster-specific latent function, and then it's got fixed covariates as well, if it's useful, and of course some noise. So just recapping basically this Gaussian process, maybe I think that's quite frequently used. Maybe you know that the whole point is to just having to, you don't want to deal with big variance, covariance matrices, and think you just want to have a kernel, something which is always going to give you a positive definite covariance function, and how many time points you've observed, and the gaps, and you have a way of specifying the covariance function of any vector of measurements, and there's different way of choosing these covariances, but a useful one which ensures positive determinateness is this exponential kernel, so which has a sort of variability around the mean trajectory parameter and a length scale which controls the smoothness. So it's just to say that this was the simplest model that we had to link to our clusters. And so again, we're using the same basic decomposition, but then we're plugging in. So, you could invent survival functions also have been incorporated in the thing. This is modular, and so you could actually generalize to, if you're interested in a particular type of outcome or a particular type of axis, this can be added in a way to the model. So just wanted to take an example of that. This time, again, it's an epidemiological study. It is looking at cognitive evolution patterns in people suspecting of having basically cognitive decline. And so what is measured, the longitudinal outcome, is results of a sort of questionnaire that people do repeatedly. And the covariates, there are both some fixed covariates, known factors, gender, education, and in particular, whether you are an ApoE carrier, whether you have one or two allele, it's known to increase the risk. So these are known risk factors. But they were interested in seeing whether you could see something in the images of the brain, and they measured volumes of some areas of the brain. So I'm not going to try to, these are really difficult names to pronounce, but anyway, they measured this volume and tried to see whether some of the decline trajectory of some don't decline, whether this is linked to some kind of physics measurement of volume in the brain. So this is just showing you the type of thing that we're measuring, volume of some area, hippocampus, cortex, and so on. So, so for this particular study, which was an American study, it's a lot of effort to do these studies. You have to follow people, you have to do these complicated measurements and so on. So you really want to try to analyze them as best as possible. They find 4 clusters. You could see 2 stable clusters at different level. One orange going down steadily, unfortunately. This is particularly weird because you're not really typically increasing your, but in fact it comes from, it's an over-smoothing of the Gaussian process, and in fact there's 2 subgroups in there, but it's been, because they seem to be more or less the brain region are functioning in a similar manner. They were put together by a bit too smooth Gaussian process. In fact, there should be one like that, and this should not remember. This is like an artifact, and another one like that. So for 2 different age groups. This is the type of thing that you could try to interpret. For example, so orange were the one going down. They have a steep decline. And you could see they have indeed the carrier of this allele, and they have low volume for 2 of the brain area, the hippocampus and this entorhinal cortex, so these 2. And the others, for the other areas, nothing special. The subject in cluster 2, which were the green one, so the top one, and the third one, which were blue one, they have stable condition at different baseline, and they differ mainly by their education status, and the other areas are quite, above average. And the cluster 4, this weird purple one, which is in fact composed of 2 groups, they all have high ventricles volumes and low volumes of the other. So this actual analysis was able to actually pick out particular region of the brain, which together was either giving a decline or was, decline or in these 2 clusters, which are the orange and the purple. Right. I've got maybe 5 more minutes. Is that okay? So otherwise I can. So I think you might be interested in that. The last example concerned when you want to cluster really large data sets. In particularly, my motivation is electronic health record. So really large data set, but these types of data, probably similar data you could have in business. So at the moment, because they are administrative data, large-scale electronic health record, in particular in the UK, but I think everywhere, they provide opportunities to uncover patterns of healthcare usage and, offer a window on the health at a very summary level, but of the health of population. And one thing which is particularly interesting and which concerns health authority is this the idea of multimorbidity is as you basically age, you accumulate long-term chronic condition, and you pick up one and you don't lose it, you add another one, and so on. And so, people, they're trying to see in a way whether you want to organize the health survey to really consider multimorbidity in a person rather than, if it's got diabetes, then it does a lot of tests in diabetes, then it's got also some heart disease, and then separately goes to the heart and so on. So they just wanted to, there's some idea of trying to see which, are there some combination of these long-term outcomes as we age. And so we wanted to use, we got together with some colleagues, Paul Kirk was really instrumental in there, with some colleagues in Birmingham, which were epidemiologists, to try to identify patterns of co-occurring long-term conditions and see which one are associated with adverse health outcome. So the data basically is a huge sort of matrix where each row is a person, and then you've, say, recorded 90 separate diseases, and you put a 1 in the column. If this person has 3 different long-term conditions, then you've got a 1 in diabetes, then you've got a 1 in heart disease, and then you've got a 1 in depression or something like that, for example. And then zeros everywhere. So you've got this very sparse, very large matrix of zeros and 1. As I say, each person is 1. And this is kind of ideal for this outcome-guided clustering because it deals very well with zeros and 1 and just discrete variable is faster than if you have multivariate normals and covariance matrixing and stuff. Very fast for actual vectors. But these are usually huge numbers. So, it could be 1 million patients you want to cluster. And however good your algorithm is, it does not going to work with 1 million. And clustering 1 million people at a time, in a model-based way is doomed to failure. Even in a deterministic way, it's pretty hard. But in a model-based way, you're doomed to failure. So, and in a way, Bayesian inference, as sample size became much bigger, there's a lot of interest in, can we have to stop doing model-based inference and Bayesian inference for these huge samples? We could only do very baby things, or can we do, is there tricks? And in fact, the tricks is, one attempt, which is sensible, is you basically split your data into shards, into separate subsets, at random, if you can, or sometime following where the data is stored, and you leave, the data where it is, and then you run your algorithm separately. So for a standard Bayesian model, which is a fixed model, you want a regression, you want a survival model, running it separately, you've got fixed parameters. There's a way you get the posterior in each chart, and there's a way of reweighting and putting things together to reconstruct the posterior inference you would have had if you did it in one go. A little approximation, but pretty good. Now, the issue with clustering, so that's the way to do. You cluster in small sets, but now the question is, as I said before, these clusters, we want to not label anything. But then to put things together, you are really stuck. At that point, you do need some matching, because you cannot put together the result of clustering in one chart and the clustering in the other chart if you do not start matching. So unfortunately, divide and conquer approaches and clustering, they don't really go well together, or turning it around, they create interesting methodological problems. So I just wanted to show you, we sort of circumvented a little bit the problem by saying it's not really sensible to think whatever you do after you've analyzed all your separate subsets, to think by putting something together you would reconstruct what you would have had if you had clustered the whole thing. Because, it's like you haven't got the same lens of your microscope. Clustering a population of 1 million, you could see very tiny things. If you're clustering a population of 1,000, even if you adjust somehow the scale of your model, it's very hard to think that you can reconstruct. In fact, I don't think you can. So we just said, okay. On the other hand, having same size subset and clustering, which are say split at random, gives you a way to see how for a particularly shard size it's reproducible. I find the same pattern again and again. So I would answer the question, so imagine I have clustered my 600, well, let's get to the example, to the last example. So we had this collaboration with colleagues in Birmingham. When we restricted to individuals with more than one long-term condition, we had about 600,000. We split that into 600 shards of 1,000, run premium, run the algorithm on each of the shards. And then what? Well, on each of the shards of the 1,000 people, we could, when we cluster, we have just a vector of probability for each of the cluster, which gives us probability of having this condition, let's say I've got 5 clusters for this chart, and these are my probabilities. For this one, I get 6 clusters for my summary clustering, and I have these vectors of probability. There I've got 8, and these are the vector of probability. Pile all of these, and then recluster. So then you could do sort of cluster of clusters. So this is what we got. I mean, here I'm not showing the 600 chart, but just a few of them, the first 80. So now each row is no more a person, it's a probability vector. Say for the first shard and the first cluster, this is the probability of having the average probability for that cluster element to have these diseases, and for the second cluster in the first chart. Then I go to the second chart and so on. And in fact, here it's been reclustered through, we've used hierarchical clustering. And there we're finding now basically four major clusters, which are, here you've got representative of all the 1,000 or the 600 shards nearly. And the first one was connected, one of these major was the conditions which you could see there are the higher black there, if you could read that, you would see they're connected with stroke. The next one are connected to heart arrhythmia. Then there's a cancer type cluster, and then a less interesting general multimorbidity where quite a few things lit up, including depression and some other disease. But what was interesting is that for the 4 large global multimorbidity cluster, we find, for example, arrhythmia. I'm just only showing you among these 80 that we've got. Nearly all of them had something to do with arrhythmia. So in each of the chart, nearly all the chart, 97% of the chart had an arrhythmia cluster. 96 had a stroke cluster, 70 had a cancer cluster. So you could actually see what would you expect in a chart of 1,000 people of that age. You have some already idea of what pattern would be reproducible. Okay. So I'm just wrapping up now there. I hope that I've convinced yourself that there's some benefit to do this joint clustering with find a clustering structure which is related to outcome, gives clues to interpretability. It can be used to investigate the risk of some complicated patterns of very highly correlated things. Because correlated clustering is fine because in a way we are making within a cluster this conditional, or we could even model if we would the correction, but it really doesn't worry us. It's not at all like a regression. There are interesting questions of how to best evaluate. Imagine in one study you find some really interesting thing, then you have another study. The population is quite different. What is transferable from one study to the other? Not the proportion of people who have, but the actual, basically, health, the prediction, the outcome. What combination would give a high outcome? People will have different proportion of covariate exposure and things, but nevertheless you should be able to reproduce the predictive part. And that for large N, clustering is really challenging because you somehow have to deal with labeling, putting together things, which you don't really typically want to do when you cluster. So we decided to shift focus, but I think it's still people are coming up with different, for example, they take a group which they add to each of the shards to try to anchor the labels. I mean, they're coming out with ingenious way of going around this kind of labeling problem if you are dealing with very large N. Okay, I'm just finished. And I welcome questions and discussions.
Do you have any questions? I have 3 questions, but if anyone else has something to ask, I will Professor Angelis, thank you very much.
Thank you very much for your interesting talk. I just want to ask about the robustness of these clustering methods.
Well, I mean, there is a model averaging going on. So, in fact, it certainly would depend somehow. I mean, if the data is weak, if it's not much data, it will depend. It will be of some of your assumption that some of the priors that you're putting and so on. But on the other hand, you are not returning one clustering. You're averaging over a lot of sort of possibilities. And that gives some robustness, in my opinion. So because basically you're doing kind of model averaging at the end of it, with respect to different clustering structures, reweighting according to how likely they are. But in terms of the number of clusters, so that's why the number of clusters is not the most interesting quantity, really. But with respect to the number of clusters, of course, if you make some strong assumptions about, how skewed it can be or something, and this DP, this stick breaking prior, sometimes tends to favor small clusters. But the posterior similarity matrix is pretty robust. And I think that's the key quantity to look at to try to understand what you've got. I repeat, the similarity matrix is basically saying how likely 2 people will be in the same clusters.
It's my turn?
Yeah. Your turn.
So I have 3 questions. One is personal, the other one is more generic, and the final one is more technical. I will begin with the personal question, which is actually, how can I remain in the green or in the blue box plots? I think I have one of the 7 or 6 criteria I fulfill, I think the education one. But I don't know about the others.
For the cognitive.
Yeah.
Well, I mean, this is not a question for me. I am not a clinician, but the only, I think definitely the latest study which come out, all seem to say that staying very active, challenging your brain is good. So I think challenging your brain, keep challenging your brain.
So the 4 clusters and the green ones and the blue ones actually show that it is true that if you keep your mind challenging, it seems that you have better chances.
Yeah.
It is true. Statistically, at least.
I mean, this is not what they had measured. I mean, they just had education. I mean, unfortunately, this ApoE allele is a strong predictor. So, I don't know anybody wants to actually know about it, but, there is a family sort of, you can inherit this ApoE, and if you have 2 alleles of ApoE, it does increase your risk. Of course, this is just an increase of risk, but I think that's just about the strongest predictor that they find. But there's also quite a lot of, they really try to targeting now protein, there's also the whole molecular aspect to try to target actually protein, which actually created these atrophies and target the things. So I think it's such an important problem. There will be something very useful by the time you probably get to that. I don't know.
Okay, the other one is that...
I'm not
statistically, okay, but if you are on the tail of the distribution, of course, basically speaking, you are on the safe side. The other one is that, Professor Richardson, it's evident that you worked for decades in epidemiology and biostatistics and things like that, and as in other disciplines like marketing, we were discussing with Leonidas here, there is an explosion of high-dimensional data. And of course, in healthcare, this explosion of high-dimensional data is tremendous. It seems that methods like guided clustering or simple clustering or other sophisticated and exotic methods are becoming more or less standardized in our days. So my question is more general. In your experience, what was actually the most exciting or more interesting or more useful application that this methodology revealed hidden patterns, hidden information that otherwise perhaps we wouldn't have the chance to find, and of course this had serious clinical results.
There's been quite a lot of environmental applications of this clustering. So my second example, because you're trying to, basically quantify areas by a lot of variables, average, ecological type variable about the whole environment, and it is really quite hard then to do regression analysis with those correlated variables. So there's been, I think, I haven't, but like John Molitor, who is particularly interested in geographical. So, there's been quite a lot of interesting geographical type environmental application of these techniques to try to understand, patterns, say, of deprivation or and how is it linked to pollution and so on, to try, maybe for public health, for kind of decision making. There's also been some application to diet. Again, diet, it's, you read, eat this and don't eat that, but, basically you're eating lots of things at once. And so what you want is really a sort of profile of diet, not the spinach is good for you, but this is bad. You need a sort of, so again, when things, this idea of a profile being, it is useful for people to try to synthesize basically recommendation of some sort. It's not just one risk factor at a time. It's really this kind of combination. So I think these are the nice application of the techniques. When we try to use it for molecular data, the issue there becomes clunk, you need a lot of P becomes really large. In epidemiology, the number of variable is moderate, is a few 20, 30, maybe 50, and you could cope with that. But when you are in molecular, you would have, so you need first to also add variable selection, which we did. When we tried to do some genetic application, I didn't have time to talk about that, but you could actually, if you give it a big bunch of covariates, but only a few are important, you could try. I mean, it is quite challenging in terms of the algorithm itself, but you could incorporate some kind of variable selection to home in on the few which are important. And I think that's an area where it requires more hands-on algorithm. I think we've got the theory, but they don't always work as well as you think, and that could be very impactful. So this is an area I think to watch.
Any other questions or comments? Yes.
Good evening. First of all, I would like to thank you about this inspiring presentation. My question is the following: in outcome-guided clustering, how do you control the risk of overfitting, especially when the same data used both to define clusters and evaluate them?
Well, I wouldn't say it's, I'm using the same data, the outcome and thing, to actually inform the clustering. So the only way you could then evaluate that is you have to have external data. You have to have another data set to actually see whether what you have found as predictive, as clusters and how they predict, you would not find the same clusters necessarily, because when you recluster something, you will find other. So that's not what you do. But you take the clusters you have, the combination, and then you see whether in this other data set they are predictive as well or not. And if they're not, it makes you think, indeed, maybe you have overfitted. You find something, but it's not reproducible. So basically, it's by taking the high-risk combination and seeing whether I'm finding, if I put this high-risk combination and I find people with this high-risk combination, are they also at risk in another data set? That's the only way you could do it. Because internally, you could split your thing in two as well and do that internally if you wanted. But of course, as soon as you split in two, you're changing your results, so you lose power. The usual thing. But ideally, take another data set, or in fact, cluster one part and do this prediction on the other part, and vice versa.
Hello, thank you for this interesting talk. My question is about the last example that you gave about clustering comorbidities.
Yes.
So, as we know, comorbidities have different levels of severity. Do you think that's what actually drives your clusters? Because we saw stroke or cancer, and then a very general, which was about multiple comorbidities. So, what exactly drives these clusters is my first question. And the second one is about okay, we have a clusters that we see nothing there. Can we take this cluster, the one with general comorbidities, and trying to find any hidden patterns within the cluster?
Yes, no, exactly. The idea is that you could sort of do that recursively. I forgot to say that the outcome there, which we chose, was death within 5 years. For that particularly. So that's why we're finding these types of, if you just took cost to the hospital, you would have something else, so there it's because our outcome was kind of a severe type of outcome. But you can, we had this massive cluster, which we just said general multimorbidity. Of course, you can again take that one as a population and redo some outcome-guided clustering in there. So we even discuss of the sort of recursive. So because at the end of the day, we had some very large clusters. And so you could try to refine them again. So you would take that one and then start again, indeed. Because it's like looking with a kind of lens, which becomes more and more focused. So you've dealt with, some things are homogeneous, but then you've got still a lot of heterogeneity. So why don't you just take that and then get with a deeper lens?
Yeah, because for me it would make sense also to take these clusters and basically stratify for demographic characteristics to see if there is anything that drives these clusters, such as like BMI or IMD that you mentioned in another example.
Yes, exactly. But you could also, on the other hand, redo that as your first clusters, because you have also got rid of clear other subgroups, so they're not messing up your, they're not finding as priority. It is still even if you have outcome guided, it is still a very ill post-problem clustering. So, you could take the big cluster and start again looking into it. But to the cancer cluster, you could take it as such, and then if you just take that one, you would find different types of but also something which didn't come up in that analysis, but we found sometimes interesting. Sometimes we find cluster where there was some kind of mental health associated with very physical things. And that's also interesting for the health service, because it just shows that some condition would benefit by, being taken care also from the mental health perspective right from the beginning, and so on.
So we thank Professor Richardson for this inspiring talk. The talk is rich for the tomorrow class of management science, because we're going to look at the case of RFM analysis, marketing analytics, and we're going to use hierarchical Keynes and Gaussian clustering.
Oh, well, that is...
Okay, so in addition, I would like to remind you that the day after tomorrow, that is on Wednesday, we have another event, the first joint business challenge with the program of human resource management with Professor Mikhail, who is here today. Thank you. So, hope to see you again the day after tomorrow at the same time here in the same place. So thank you all for your...
Yes, thank you for coming so late. I mean, it's a long time I haven't... It's a long time I haven't given a talk so late in the day, I must say. Maybe quite unique.
Thank you again.
Yeah.
I'm not sure that do we have a QR code for today?
Yes.
We have. Because nobody leaves the room before scanning the QR code.
You have codes all the time to see who is there and so on. Is that it? Yeah. I need to. I mustn't go to dinner with the.